first speaker of this closing session is Andrew Huxley from the University of Edinburgh. He will be telling us all about extended non-fermi liquid states.
Thank you very much, and thank you to the organisers for what's, for me, been a very interesting and diverse conference, even though...
Here to make up this kind of
An interesting and very... Is that better? Yeah. Okay. Interesting and very diverse conference, despite the focus on a very apparently specialised subject of strange metals. So here's my list of collaborators, the people that actually did the work. So I should mention the first three that I've highlighted. The first two did the experimental work, Chris and Neil especially, and there's theory input from Frank Kruger from UCL. So the theme of my talk is something that I think everybody here will understand and appreciate, that we're used to dealing with quantum critical points where we have this non-fermi liquid behavior that narrows down as we go down in temperature to a point which is crossed with a tuning parameter such as the pressure. But there exist very few examples of materials where there's an extended region of phase space where that non-fermi liquid behavior exists down to close to zero temperature. In fact, the best example that I'm aware of is manganese silicide, where a T3/2 power law is seen from a critical pressure of about 15 kilobars up to at least double that pressure. And that really does extend all the way down to low temperatures. Of course, there are other examples in low-dimensional examples, and perhaps one or two other materials that I could list, but there are very few. Rather than go through a sort of general description of those examples, I wanted to focus on a new material that we've been working on in Edinburgh, and I'll talk about uranium dioride, uranium gold 2. It has a very simple crystalline structure. That was one of its selection criteria, to be hexagonal. If we refer to what the structure looks like, it's columns of uranium atoms, which are these sort of bluish atoms in the picture, arranged on a triangular lattice. All right? There's just one atom per unit cell of uranium. And the separation of the atoms along the columns is rather short. So in Silke's talk, she talked about manganese, and when the distance was short, you had itinerant type behavior, and when it was long, you had localized moments. So there's a similar distance for uranium distance of 3.5 angstroms that's commonly called the Hill limit. So you might expect the electrons to be delocalized along the chains, and perhaps more localized when looking in the plane, based on that rather simplistic and not very substantial criteria. This sort of summarizes what was known about the material when we started, apart from the structure, was that the susceptibility and there's some sort of transition there at 43 Kelvin. And it was this, these are our measurements that I'm showing here, but it was this anisotropy of the susceptibility that was the motivation for our study. You might not see why that was, but I'll come back to that at the very end of my talk if I have time. So I was interested in the fact that the susceptibility showed that the moments were pointing along the c-axis, and that the c-axis susceptibility is larger than the a-axis at low temperature. What's plotted there is 1 over chi. So the culmination of a lot of neutron scattering and X-ray work was that we established what the phase diagram was. So first of all, what happens at low temperature and high magnetic fields? That's the easiest to understand. So you've got the triangular lattice with 3 sites, A, B, and C. Along 2 of those sites, the moments would be pointing parallel to the field, and along the 3rd site, it would be pointing anti-parallel to the field. So it's a ferromagnet. That's in that little region up at the top at low temperature and high magnetic field labeled F. But the vast part of that phase diagram is covered by what I've called the delta state, where the system is modulated, or the magnetic structure is modulated along the c-axis. And that structure for the delta state is shown in the right-hand picture over here. And what's important there, you can see that there's some element of frustration coming in. You can see planes of atoms where you've got spin up, spin down, and almost no spin at all. And what happens is you cool the material down, rather than the moments squaring up to take their full value, the modulation remains, as far as we can tell, sinusoidal. So what we have to explain is what happens to the moments on these sites where it would be small. So first of all, if we look at the intensity from some of those magnetic Bragg peaks seen with neutron scattering, we see that that follows a fairly conventional sort of form. I've drawn a sort of BCS line through it. So this is the order parameter squared. Nothing special going on there. And in particular, you'll notice that the magnetic moment is saturating towards a constant value at low temperature. And in fact, we've measured down to millikelvin temperatures, and there's nothing more happening at lower temperature in that figure. However, we can also see the magnetic order with X-rays by doing resonance scattering. But if we go away from resonance and we put up the intensity an awful lot, we can see that there's some charge order as well. So this charge order I've labeled charge density wave here. It occurs at a wave vector that's twice the spin density wave vector, but it has a very different temperature dependence, a very different characteristic temperature. So one source of charge modulation is simply magnetostriction, right? And that would go as the magnetic modulation squared. So that's why I've drawn this extra line here, which is just the square of the line above. So it's clearly not coming from that. And the most important area to focus on is here, where the magnetic intensity is constant, but we've still got a very strong temperature dependence in the charge density wave. So a conjecture would be that what we're seeing here is the condo screening and a charge transfer associated with a condo screening of those moments that have to disappear. Okay? And because we're looking at a periodic structure, we're using the power of diffraction to amplify that signal. And that's why we see it. It's a very small signal. And this charge transfer is something that's probably a little bit controversial. I did talk to Pierce. Unfortunately, he's not here about it. And his view was that, yes, it should be there, but it should be of the order of the condo temperature divided by the Fermi energy. All right, so very weak, but we're at a synchrotron, so we've got lots and lots of flux. Another thing I should emphasize is that both the spin density wave and the charge density wave, they're commensurate with each other, but they're incommensurate with the crystal lattice. They might be driven by some kind of nesting feature in the Fermi surfaces. This is density functional theory calculation without magnetic order in the calculation. And that period of modulation changes as a function of temperature. So if we've got condo physics, let's see what happens in the macroscopic properties of the material. So what I've got at the top is the heat capacity. So there's a big Schottky-like peak in the heat capacity out at around the Néel temperature, which could be indicative of some crystal field levels, although in uranium one never sees crystal field levels as clear excitations in neutron scattering. But what's interesting is what happens at low temperature is what we find here is that C over T is increasing as the temperature decreases, and it's a logarithmic temperature scale here. So C over T is going as log T. And there's about a half R log 2, depending where you choose to integrate this up to. If we look at the susceptibility, need to do measurements down to lower temperature, but those are the ones going down to about 1.8 Kelvin, we see that mirrors the heat capacity and with a Wilson ratio of around 1. So it looks like that's also coming from electronic degrees of freedom. Finally, if we look at the resistivity, what you might have noticed was that the charge density wave, if you like, the sort of condo temperature scale was about 20 or 30 Kelvin. There is some feature in the resistivity at about that temperature, as well as at the Néel temperature. And then at low temperatures, what we find is that there's a non-Fermi liquid exponent. But if we go down to the very lowest temperatures, below about 200 to 300 millikelvin, that does seem to cross over to a T squared in our case. Let's have a look at the heat capacity in just a little bit more detail at the very low temperature heat capacity. So this is the C over T plotted against temperature, again with the temperature on a logarithmic scale. So you see this log T dependence of the heat capacity, but the striking thing is at very low temperature there's a 1 over T cubed upturn, and that's coming principally from nuclear quadrupole moments to do with the gold, and a little bit of uranium-235. All right. The actual magnitude of that contribution we can calculate from the DFT, because we know the electric field gradients or the electric fields at the sites, and it fits very well within the sort of precision that you might expect, within 10%. It's interesting to compare the log T heat capacity that we see in zero field with what we see in field. First of all, when we apply field, it makes almost no difference. All right, the different data applying field along different directions is shown there, until we apply sufficient field that we collapse into this ferromagnetic state. In the ferromagnetic state, we lose the log T completely and we go back to a Fermi liquid. C over T equals a constant. So when we see a log T heat capacity, one of the models that we could compare this with is the two-channel condo effect. In the two-channel condo effect, we get a log T. So if this is the C over T, I take off the nuclear components. This is the data now just with a 1 over T cubed subtracted, the blue points. And the red line is a calculation for the two-channel condo effect in magnetic field of 0. But what you know about the two-channel condo effect is that there's a residual entropy at low temperature, and as soon as you apply a magnetic field and split the two channels, that entropy gets released. And so the same calculation would say that when we applied 1.5 Teslas, we'd get the green dashed line. All right, and we clearly don't, because there was no change in the heat capacity at that sort of field. What we could do is we could use that entropy release and assume or take the model that there's a distribution of the temperature scale over which we get the entropy release. So if we take the uranium 4 plus and uranium 3 plus as an example, and then we were to split the uranium 3 plus, and the splitting would be due to the applied field, but also the exchange field that's coming from the magnetic modulation. All right, so if we put that magnetic modulation in there, we'd get a distribution of the energy scale or the temperature scale over which the entropy release happens. And if we took a realistic model for what that distribution was, we can explain the log T heat capacity. So it's a little bit like Miranda's model for a distribution of condo temperatures for the normal condo effect. So that would explain nicely the independence of C over T from the applied field, because that's just shifting us up and down within our sine wave. But there are some shortcomings, namely the actual distribution we have to take is Ts proportional to m, whereas the one that would be given theoretically would be that the temperature scale goes as the field squared, or m squared. So a different or more careful consideration is required. What I want to go on to now is to give you some more experimental background to this material and what happens when we apply pressure. So when we apply pressure, we suppress the antiferromagnetic or the spin density wave, and we can suppress it completely in a pressure of about 3.2 GPa. When we suppress the magnetic order, what happens is we get superconductivity, but some very interesting things happen. So I should be thrown out of the conference for what I'm about to show you. So we're going towards a quantum critical point. So these curves are increasing in pressure as we go down. And the non-Fermi liquid bit that we're happy with, which is a non-T squared resistivity, is becoming less and less important until we get to the critical pressure, which is here, where we get a perfect T squared resistivity. So it's exactly the opposite of what we're used to. And if I plot this in a different way, so I'm plotting here the temperature above which we get a departure from the rho 0 plus AT squared as the points, and I'm also plotting 1 over the square root of that T squared coefficient, which is something that we'd expect to be proportional to the coherence temperature. And we see that the coherence temperature approaching the quantum phase transition, rather than coming down, is going up. So that's very unusual, and then we get this perfect T squared term right at the phase transition itself. So what this is telling us in simple terms is that the non-Fermi liquid state is associated with the magnetic order and not with the quantum critical point, or the transition might well be first order, but not with a weak quantum criticality associated with the suppression of the antiferromagnetism. These aren't my final conclusions. I've got a couple more slides to show you. I don't know how much more time I've got. 5 minutes?
5 minutes until the question time.
Yeah, that's okay. I want lots of questions. So what I've shown you so far is uranium gold-2. It has a robust non-Fermi liquid state. We might call it a marginal Fermi liquid because it's a log T heat capacity, and it's robust against magnetic field. Magnetic field didn't move it. We saw evidence for charge transfer coming from this charge density wave that is evidence potentially for condo physics. And the non-Fermi liquid state was linked to the magnetic order rather than linked to a quantum critical point due to the suppression of magnetism. And we saw this very unusual T squared resistivity right at the critical pressure. And actually, there's a very unusual T squared resistivity also in MNSI at the critical pressure, that other example that I gave you there, where there's a very large T squared coefficient right at the critical pressure. I also showed you some superconductivity. So I'd like to say a few words about the superconductivity, just a couple of graphs. So here's the upper critical field for superconductivity at the highest pressure, where the transitions are the cleanest. And they're shown there for the field along two different crystallographic directions, along the c-axis and in the basal plane, along the a-axis. And the solid lines there are BCS fits, which are determined essentially just by the slope of the Hg2 curve at Tc, but with no paramagnetic limitation. If I put the paramagnetic limitation in with a G factor of 2, as usual, then I'd get the dashed lines. So the data is clearly exceeding the Pauli paramagnetic limit. And more surprisingly, it's well fit by weak coupling BCS. Right, so that's rather a big surprise. So because it exceeds the paramagnetic limit, it suggests that the superconductivity may be spin triplet. But things get even more interesting if we start to rotate the magnetic field from the c-axis down into the basal plane. So what you'd normally expect, if you're close to Tc, would be that you'll get an effective mass anisotropy. An effective mass anisotropy is something that would be a monotonic dependence, i.e. there wouldn't be a minimum or a maximum. But what we see experimentally is a very deep minimum. It's hard to explain that minimum, but one way you can explain the minimum that persists to TC, the individual curves are shown in the panels below, is if you have a two-component order parameter, right? Like a two-dimensional irreducible representation. I won't bore you with the details of the theory. That's the free energy. You've got a lot of gradient terms, and for a lot of values of those gradient terms, you get a minimum in He2 between the field parallel to C and in the basal plane. If you want a quick explanation of why that is, when the field is along the C-axis, the order parameter has two components, is 1 plus or minus I. Right? When the field is in the basal plane, the order parameter is 1, 0, or 0, 1. Right? So the order parameter changes as you change the field direction, and that change in the field direction can be in the opposite sense from the mass anisotropy. And putting those two things together can give you the minimum. So putting these things together, it suggests that we have a spin triplet, two-dimensional irreducible representation. Here are the two possibilities for hexagonal symmetry. This is the same character table that you'd have for UPT3. UPT3 is E2U, if you believe Jim Salz, and I do. But the E2U he chooses is the one with the D vector parallel to the C-axis, because he sees, or we see in UPT3, paramagnetic limitation when you put the field along the C direction. Right? So the D vector, which is the direction of spin zero projection for your Cooper pairs, is along the C-axis in UPT3, whereas we see no paramagnetic limitation, so we're going to have to put D in the XY plane, which are these two. That leads to some important differences. So when you put the D vector in the XY plane, that means the superconducting state is nematic, i.e. it breaks hexagonal symmetry rather than breaking time reversal symmetry. One of the consequences of that, all right, within the BCS theory, within weak coupling theory, is that what we should see is a splitting in low magnetic field of vortices into half quantum vortices. All right, I hadn't seen it because doing experiments at 3.5 gigapascals is tricky, so I can't just look with an SDM. So here's a summary of the superconductivity. We've seen weak coupling BCS describes that upper critical field with no paramagnetic limiting. That suggests that it's a triplet or odd parity state. We saw this unusual non-monotonic dependence of Hg2 with field angle that is consistent with the order parameter having two components. And we've suggested that the actual superconducting state, although at first sight it might look similar to UPT3, is actually very different because of this different choice for the D vector direction. And it's very interesting because of this possibility of it hosting half quantum vortices. That's the end. Thank you very much.
Time for questions?
So how do you understand the moment differences as you go from layer to layer? I mean, it's all, you think about the moments on each of the sides or in the local environment.
Yeah. Okay. So we can model the magnet. You're talking about the magnetic structure. Yeah. So we have a model for the magnetic structure, which is essentially we put in an antiferromagnetic exchange in the plane between nearest neighbors, and then we put in an RKKY type interaction going along the C-axis. All right, and with that model, we can get this particular state.
Also, so you think it's basically a nesting type of picture? I mean, RKPY, you use the nesting type of picture.
Yes. So I don't know, but that we have identified, potential nesting vectors in the Fermi, the Fermiology of the material. Although actually, what we do is in the DFT calculations, you have a U parameter, or something similar to a U parameter, and we adjust the U parameter until we get a nesting vector that agrees with the experiment. Thereabouts. Yeah.
Hi, great talk. I'm interested in this uranium aluminum uranium gold 2
Yeah.
charge density wave,
Yeah.
which doesn't go like the square of the spin density wave.
Yeah.
So you reference that in the context of magnetostriction, which some people say. So the statement that the charge goes like the square of spin it's much broader than just magnetostriction, right? That comes from the fact that one is a scalar and the other is a pseudo spin. So if you put them into a free energy, they have to go like rho s squared to get a skid. It's much broader.
Yeah.
To get something that's not rho s squared, they have to be coupled in a way that's very. Let me ask a more concrete question. If you take a higher power,
Yeah. If you
is there
see,
any way to get them to match?
if you take it, it's never going to work because the
If there are symmetry constraints from Landau theory on how those things are allowed to couple.
yeah. So I could give a kind of a personal suggestion or interpretation. If you take because it's flat down here, whatever power you take, you're not going to get something that's changing strongly for the charge density wave. Now, the magnetostriction contribution, it might be there, for example. So you could imagine that there's a very small signal here coming along at 0.05 level that's coming from the magnetostriction. And then on top of that, you've got this condo scale that's coming in, that's doing this charge transfer that's coming in at a temperature of around 20 or 30 Kelvin. And what we saw in the resistivity was the resistivity had this very clear signal at around 20 to 30 Kelvin as well. So that would be a personal kind of go.
The charge and the spin are coupled, but there's more than one coupling mechanism.
There might be more than one mechanism giving the total charge density wave. The dominant one might be independent of the not completely independent of, but a different mechanism from the spin density wave. It's not driven by the spin density wave. Yeah.
So then the next speaker should
Sorry, I didn't fully understand your charge transfer from the condo. Can you have a simple cartoon? What's happening?
Yes. Well, a wrong simple cartoon would be
Wrong is better than right.
would be that in the condo effect, you pair a conduction electron with the local moment to form a singlet. So that conduction electron, its proximity to the local moment is then different from what it would have been had it been a completely free itinerant conduction electron. All right, so there's a small charge accumulation, might be positive, around on there's a condo length scale, right? Just the Fermi velocity and the condo temperature give you a length scale. So that would normally be the size of the singlet. So you can imagine that's giving rise to a small change in charge.
That's single impurity imagination, no? Isn't it? If you have a lattice, would that still make any sense?
So then we're seeing the lattice is on the length scale of the density wave, of the spin density wave. So it's a long period lattice. So it's potentially, the lattice spacing is as large or larger than the condo screening length. That's it, yeah. Doing the calculation for a real lattice is, of course, a difficult theoretical problem. So this is just a little bit hand-wavy. Yeah.
Beautiful talk. I was curious, the resistivity flashed by under pressure quickly. And,
Yes, okay.
And I guess it looked a little filamentary initially,
The superconductivity looked a little filamentary.
Yeah.
Yes.
and then where
Whoops, I've gone zooming past that. Yes, so here we go. So yes, so in the magnetic state, so up to at 1.3 gigapascals, there's no sign of any superconductivity. But then here you see there's a departure from my green dashed line. But it's not a complete superconducting transition. So it suggests the transition, the actual data that I showed the HE2 curves from were at higher pressures than what I'm showing on this particular figure, where the transition is much cleaner and goes to zero. So
this is still in your delta phase.
3.22 is in the delta phase, or just at the borderline, or just tiny bit above. 3.72, where we're already getting zero resistivity. You can't see it, but there's got little points along there. That's above, and then the transition. I mean, you can see that there's still two steps there. It's not a nice transition, not the sort of transition I'd love to be showing you. But at higher pressure, it then becomes cleaner. Yeah.
All right, if there are no further questions, let's thank the speaker.
Thank you.